So good morning, everyone.
Good morning. Good morning.
Now we'll continue from where we stopped last yesterday, and we talk about the measurement of the interference signals. So since the interference signals can be either conducted or radiated, the propagation along the paths, that is the conduction path and the radiation path, can be detected by measuring interference currents and voltages. The interference effects in their immediate vicinity are commonly referred to as a magnetic or electric coupling. That is, if we are in the near field of the signal, then we'll be having either the energy stored in the magnetic field or energy storage in the electric field. So these are assessed through a measurement of the magnetic and electric fields in the near field, just like we were looking at the near field of an antenna, so to speak. So at high frequencies, the equipment dimensions will be of the same order of magnitude as the signal's wavelength. And therefore, the interference energy is then going to be primarily a radiated one, because as we have seen in our study of the antenna, then an antenna will radiate most efficiently when its dimensions or the large dimension of the antenna is very close to or is of the same order of magnitude as the wavelength of the signal on it or exciting it. So radiated and conducted interference energy must then be taken into account when we are testing the susceptibility of a victim equipment. That is, an equipment that is susceptible to electromagnetic interference or EMI. So interference sources such as signal wave oscillators as well as pulse generators are then used to generate known amounts of interference so that the measurement can be done. This is exactly the same way you would test a communication channel by generating electrical noise and then passing it through that channel and measuring what the noise, the SNR at the end of the channel. Or even when you are testing a system such as an amplifier and the likes, you still excite them with known amounts of noise to see how much noise will be appearing at the output of that amplifier. So a test setup for the common mode current measurement would have the following form, where we have the source of the interference with its source resistance, then we are sending in a current to the scope, which is just a transformer, and then we pass that current through a load, and we take the value of I2 that is coming out of the transformer, and we get a value of ICM, or the common mode current, as I1 minus I2. Okay, and then on the ground plane, of course, we have the two LC circuits to give us a decoupling of our values here. That is, we are floating the measurement test from the ground plane. So differential mode currents would be measured with the same setup if one line is then wrapped around the transformer at least once. That is, we can make a loop around the transformer once, and then we'll be able to measure the differential current. So common mode currents can be measured during the design stage, and emission from most devices will then be dependent on the magnitude of the high frequency currents on the cables and the PCB tracks, especially if your system is a digital one. We know that a square wave will be a Fourier series of an infinite number of sinusoidal harmonics. So as a rule of thumb, the maximum allowed common mode current must be less than 5 microamp at a distance of 5 meters from the common mode source. This is as a standard. So in general, this then means that the maximum measured emission must be less than or approximately 30 microvolts per meter, and that is the electric field intensity, so to speak. So the magnitude of the electric field intensity at a distance r from a common mode current, where we are now going to assume that we have a far field kind of effect, where the radiation or the intensities are varying no faster than 1 by r, as you recall from our antenna theory, then it means that the magnitude is going to be given by the 60 coming from the eta, if you recall, divided by 4 pi r there, 4 pi, then ICM and divided by r. So we have divided all through. So this 60 came from the impedance, the intrinsic impedance of the medium, and of course divided by those other values that we already have seen in the antenna expression. That is, you can recall from the dipole antenna, and then you can use that to get this value there. So emission may be due to capacitive coupling between the lines, that is when you have two parallel lines, or from a line to the ground. So common mode currents cause unwanted radiation and can be suppressed by placing a choke, that is a large inductance, or a clamp such as ferrite beads in the current path. So for those of us who will be doing a high frequency electronic system design, these are important techniques to keep in mind. A ferrite bead is a ferrite that is made in form of like those beads of the Maasai whatever they call necklaces and the likes, but they are made of compacted ferric oxide particles that is sintered, and then with a hole where you pass through the lead of your components through the beads, and then they concentrate that field, the magnetic field, around the component rather than letting it leak away. So digital ribbon cables, I'm sure for those of us who have opened a computer, you'll see a flat cable with many parallel lines. They are called ribbon cables. This can give significant problems with common mode current radiation, and clamps may be the more feasible approach to suppress radiation from such kind of digital ribbon cables, because some of them will be signal lines, others are grounds, and they are all over, spread all over the flat cable. We note that ferrite beads or clamps will have no effect on the differential mode radiation, however. So For the differential mode currents, the far field magnetic field will be related to the far field electric field intensity as H equal to E divided by eta. And we saw that this was the E theta divided by H phi when we are looking at in the spherical coordinate system. And the symbols, of course, I mean they carry their usual meaning, that H represents the magnetic field intensity and E represents the electric field intensity, while eta is the intrinsic impedance of the medium surrounding. So the H field is usually measured at 0.1 meters from the differential mode source, and the electric field usually at 3 meters. So this constitutes the legal length of cables that may be supplied by this with the consumer product for operations at frequencies below 16 to 300 megahertz. Okay, that is the length of cable that you have on your computer, that is that you connect to the power cable, is a standard length, and this is stipulated by the guidelines. The high field can be measured using a current loop that is made out of a coaxial cable in which the outer conductor is removed and a 50 ohm chip resistor connected between the loop formed by the inner conductor and the jacket, that is the outer conductor. So the H field then induces a voltage across that resistor, which will be measured by the measuring system. So the sensitivity of the probe is usually high at low frequencies, but becomes independent of frequency above about 300 megahertz. So this will be because while the voltage will be increasing with frequency, the inductive impedance of the probe will be increasing in the same direction because of the skin effect, and therefore preventing any further increase in the current. That is, the current detected or induced in the loop now saturates. So the E field measured at a distance 3r equal to 3 meters from the source may be related to the 0.1 meter electric field as E equal to 2.7 times 10 multiplied by the frequency and multiplied by the magnetic field intensity. Okay, and the F will be measured in hertz. So the measurement setup for the H field is as shown below. This is the probe we are talking about, and in between the probe, of course, we'll cut out for a resistor, and then we'll place it above the plane of the circuit. Here we have deliberately used digitals, ICs. Okay, that is, we have IC1 and IC2. They are connected in that form, and we get a value that is, this is just a resistor part of the system, and so forth. And therefore, we are trying to measure how much the radiated magnetic field will be obtained from this particular circuit. The mechanism involved in conducted interference will be as shown below. So we have the wires, of course, they're usually having like a screen, which is usually grounded. Such kind of a screen, of course, it would be a conducting plate or what is it called? A box. And this is usually called the Faraday cage. And then we have, of course, capacitors, which are parasitic, okay, between the generator, and this is where the interference is coming from. Again, the disturbed element, of course, has its own casing as well, and it has the same parasitic values with that. And we are representing that equipment with a load resistance R, which is usually the input impedance of that system. So the interference, we have a common mode interference and also a differential mode interference there, and we also have that there. This is at the wrong place, should be at the bottom here. I will correct that. So a floating interference source, by floating we are saying that the interference source is not grounded, is not connected to the ground plane, will emit a primarily differential mode interference, which then will propagate along the connecting lines by conduction. So the interference current flows from the emitting source toward the victim on one conductor and returns to the source from the victim through the other conductor. And the differential mode interference is usually important mainly at low frequencies, as we saw yesterday. So parasitic capacitances in interference sources and the disturbed equipment or intended ground connections will lead to interference currents also in the ground circuit. Because we know that no ground circuit is going to be perfect, we have resistors in the ground itself. We could also have the skin effect issues of capacitors and inductors there, and therefore the voltage, that is a potential difference between the ground point of the victim to the ground point of the source, will introduce a voltage drop, and therefore we can see that that will generate some kind of interference voltages, so to speak, because this will be sinusoidal as well. So common mode currents will flow toward the disturbed equipment through the connecting conductors and will return through the ground connection. So a parasitic capacitive impedance will then tend toward short circuits at high frequencies, and therefore the coupling effects in the connecting cables and the equipment itself will increase with frequency. So common mode interference currents become dominant in the megahertz range, and asymmetrical interference, which consists of both symmetrical and differential mode and asymmetrical common mode components, and crosstalk will occur when the coupling path between the EMI source and the victim is short. That is, the two of them are very close together, and we can have, just like the way you have mutual inductance when you have two coils in close proximity, then crosstalk would occur when you have two lines that are close together as well. Examples will include things like the source and victim sharing a common impedance, which then will form the path for the crosstalk signal. An inductive or capacitive coupling through the magnetic or electric fields, respectively. That is, we can have two lines which are coupled edgewise because they are parallel and close together, and therefore there will be a capacitance between one line and the other because of differences in potential. Okay, so we have a potential difference between them, and that will introduce a capacitive effect between the lines. Okay. Because of the current flowing in the lines, of course, there will be magnetic field from the ampere circuit or law, and that introduces the inductive coupling effects. So crosstalk must be addressed when we are designing PCBs or multi-cable assemblies. That is, no two parts of the very straight lines. Okay, if you want to cross lines, say for example, when you have a multi-layer kind of PCB, you want one track to cross the other track that is below it at most ideally 90 degrees, and then we'll have no coupling. Then coupling will be lower. You don't want them to be parallel. So crosstalk can be modeled as a network with an impedance ZK. This should be Zm, not Zk, common to both the output and input circuit as shown here. That is, we have the source impedance there for the source 1 and the source impedance for source 2, and they are sharing a common path with a mutual impedance Zm, and therefore this would be the load 1 driven by Vs1 and the load 2 driven by Vs2. This gives you a nice, it just jogs your memory to your circuit theory in the third and the second years, okay, the ECT that you dealt with. So the currents in the two circuits will flow through Zm to the interference node, which is usually the circuit ground. And by superposition, the voltage established across the load ZL2 by the current from Vs1 is therefore going to be given by that expression there. That is, you know how to apply superposition is that we replace one of these signal sources with its internal impedance, okay, and try to look at the current that would be flowing through the circuit when on the other signal source is acting alone. And therefore, we have only the VS1 acting, and the VS2 has been shorted ground to ground. So we can show that. That is, we can connect this one with a short circuit. It will be replaced by its internal impedance, and then we'll see that the VS1 will be driving ZS1 in series with its load ZL1, and this will be driving that a parallel combination of Zm and ZS2 plus ZL2, and this gives us a value of that nature there. So, while this ZK is unfortunate, I think I should change that in the diagram and put it as ZK rather than Zm. So we'll put this as ZK is small. We can then write that the ZK multiplied by ZL2 divided by ZL1 plus ZS1 plus ZL2 plus ZS1. This is the transfer function, the voltage transfer function of that circuit when we have only one of them operating, so to speak. Here, what we have said is that ZL2 is much larger than ZS1, because when you are making a voltage source, of course, you want its source impedance to be small. Therefore, ZS2 is going to be much smaller than ZL2, and therefore just have those values there operating. So crosstalk will therefore depend on the mutual impedance or the impedance of the connecting path or the common path, and will decrease as we decrease the value of Zk. So if Zk represents the impedance of the ground plane, that is the resistance of the grounding path, then we must go to as near perfect conductors as possible. So the effect of crosstalk on the signal will be specified through distortion, a distortion ratio that is defined as the voltage drop across the load when the Zk is equal to 0 to the resulting drop if Zk is not equal to 0, which is a practical whatever case. And hence, we can get that is VZL2 with Zk equal to 0 over VZL2 with Zk not equal to 0 but small will be given by ZS1 plus ZL1 over Zk multiplied by VS2 over VS1, and that defines our distortion ratio. So if ZS1 is a 10 ohm, has a 10 ohm resistance, and ZL1 is a 50 ohm resistance or termination, then Zk is 0.1 ohm, then we can see that VS2 by VS1 is about 0.01, and the distortion ratio is about 15.5 dB. So Zk may be lowered in the following ways. We can use two conductors rather than just using one, and then we then connect whatever that is with the lead will be shortened. One thing is that the resistance of one conductor and the resistance of the other will be in parallel, and we know that when you have two resistors in parallel, the resultant resistance is lower than the resistance of the any of the two conductors. Two, we can use low value or low Zk conductors, e.g., by dedicating a layer of the PCB as a reference plane. How do we get a low Zk? Is by making sure that the conductor we use for the ground is much bigger, or it's much the cross section is much larger than the signal whatever conductors. Then we shall be reducing the value of the impedance of those conductors, so to speak. So we can use a galvanic separator, that e.g., an isolation amplifier, or an optocoupler between the two circuits. That is, instead of connecting them through the same path, we can use an opto transistor, so to speak, which will take one signal from one side to the other. Or you can use an isolation amplifier, which has a very high, it provides a unilateral kind of flow of the signals. And the signals flow only easily in one direction and in the other. And therefore, that's where we need to recall our topic from the differential amplifiers that we covered in the third year. So crosstalk can occur through radiation as well, either capacitively or inductively, whereby the capacitively coupled crosstalk signals will be transmitted in the form of electric fields. So a possible circuit model for capacitive coupling between two circuits in close proximity is as follows. Say, for example, in many cases, you would be having, say, for example, you have, say, a digital circuit A, and you have an analog circuit B, but because they are very close together, and they are at different potentials, that is, if we can have a potential that is at this point is different from that there, we have a capacitive effect. And that will give us a coupling capacitance CAB. And this therefore gives us a value that we can look at this circuit as follows. We have circuit A, and we have circuit B, and we have that value there of CAB connecting the two. So the ratio of the load to the source voltages is then given by VL by Vs equal to J omega 2.5 omega CAB and multiplied by the load ZL, which is the circuit B impedance. So we therefore deduce that capacitive coupling will behave like a high-pass filter and will increase with the value. Okay, the coupling will increase with the load impedance. The crosstalk will depend on the ratio or the the voltage transfer function VL divided by Vs. Crosstalk signals are in phase with each other, and two PCB traces at different potentials will therefore form a parasitic capacitance between them, whose magnitude will depend on the ratio of the length of the two traces to their separation. And for those of us who will be dealing with breadboards in the lab, we can see that we can always take those two to be like different circuits if you have, because many of us usually try to put them as very far together, and then we are trying to feed them with tracks, small wires. We can be introducing this kind of interference. Another thing is that many of us will make, say, for example, a clock circuit using the popular student popular timer circuit 555 timer, and we place it on one section of PCB. Then we get another section of PCB and make another, say, for example, the Arduino board, which will be driven by these clocks. Okay, and then we have another third PCB again somewhere, and then we try to connect them together. This is a recipe for disaster, especially when you have to worry about interference. So to our first order, for PCB traces of width W approximately 0.003 millimeters, or about 3 microns, the length L and with a length L and a trace separation D, the capacitors that we can get there will follow the parallel plate capacitance and will be given by the area, which is W multiplied by A epsilon by D picofarad. Of course, if they are age-wise coupled, then the values we'll be dealing with is, of course, the height of the height of the trace. So capacitive crosstalk can be minimized by keeping the CAB low. That is, we use a larger trace separation, or we reduce the surface area over which the coupling occurs. So rather than put two traces above one another on their broad ends, you make them to run edgewise. That is, the only coupling is between the edges. Therefore, the T, that the thickness of the trace multiplied by the length will be smaller than the width of the trace multiplied by its length. Okay, and therefore CAB will be reduced. Another thing is to separate them widely, but don't forget, when you are dealing with a circuit board, you also are limited to the size of board that you can get. Okay, you want to keep your function smaller, okay, as small as possible dimension wise, and therefore what happens is that the separation will not be as wide as you would like to. So shielding, we can do shielding around one or both conductors, okay, when any of this is not possible. By shielding is that we place a conductor around one of them, such as is done with the coaxial cable. So we'll put a conducting whatever cover on one of them and ground that value down, and therefore the interference from the other line will be shorted to ground through the cover. So magnetic coupling will dominate inductive crosstalk, and this can be compared to a transformer action whereby the voltage transfer ratio is going to be given by minus J 0.25 omega multiplied by the mutual inductance M divided by the load resistance or the load impedance ZL. So M is the mutual inductance between the two coils and will be as shown below. So we have circuit A and we have circuit B there, and we have a distance Rx and a distance separation D1 in circuit 1. And therefore magnetic crosstalk, of course, would be like that. That is where we have a source driving one of the circuit, and then the mutual inductance between the inductance of this, that is the magnetic fields around these lines coupling, will give us a mutual inductance there. And this is a conceptual view of this particular circuit there. So inductive crosstalk has a high pass characteristic, as in the case of capacitive crosstalk. A level that increases with decreasing load impedance for the same amount of coupling M, and in undesirable source and load voltages Vs and Vn that are out of phase, unlike with the capacitive crosstalk. So inductive crosstalk can be minimized by, one, we increase the conductor separation so that we can use the 1 by R decay of the field intensities. Two, we can twist the sending and returning conductors about each other where applicable. If you look at power transmission circuits or lines, you will see that although the three-phase ones, they go changing whatever their position on the pylons as you go along. That is, the line is not, they are never done parallel to each other, but they'll go crossing somewhere as you go along between the pylons, so to speak. That is phase A, the yellow phase, the red phase, and the blue phase will not be connected on the same spot or on the same position at two different pylons, so to speak. This is usually done to reduce the inductance of the transmission line. So twisting, you have seen maybe if you opened, say for example, some of the old telephones, you'll see two wires, two parallel conductors that are twisted together. Okay, that twisting is so that the electromagnetic or the magnetic field on one conductor will cancel the magnetic field on the other because of that twisting, as they are changing position, their spatial position relative to each other. So, as shown, the magnetic field at X generated by the current in the conductor of circuit A is given by H equal to IA by 2 pi D1 by Rx squared, whereby X, we are talking about this value that we have here. That is, we are talking at this point X, and we are trying to look at the magnetic field around that point, because it's the magnetic field of this circuit that will induce currents or voltages into this circuit B here. So IA is, of course, the current in circuit A, and it is therefore necessary that each circuit uses its own conductors. They should not use the same conductors, so to speak. So conductor separation within a circuit must be kept as close as possible to reduce the loop area threaded by the current. We know that any induced voltages will depend on the area threaded by the magnetic field lines. And therefore, we must bring these conductors of a given circuit as close together as possible so that we can reduce that loop area. And this will happen also when you make your circuit on the PCB. You don't want to make the currents go very long distances, okay, such that they make a big cross-section area. That is the forward current and the return are following very large paths, therefore describing a very large area through which the magnetic field lines can thread. Okay, this will increase the induced voltages or the interference voltages as well. We must use small resistor in the signal and or the supply lines to try and drop some of the whatever the voltages, so to speak. So only the necessary bandwidth required by the particular application should be used. I'm sure from your studies of digital circuits by Professor Mwangi, you are told that you want to make your clock to be as sharp as possible, and you are even advised to use Schmidt triggers to try and make the levels of the, the fall and the rise times shorter. Well, in terms of EMI or the EMC, that one is very dangerous because the fast dropping or the fast changing edges of the clock will represent frequencies from DC to infinity, that is to very, very high frequencies when you look at the harmonics. And therefore, it's necessary that we reduce the rise time and the fall time. Well, the digital circuit engineers are right. Of course, you need a very sharp fast because you don't want, some of the times you may not be able to recognize what is a pulse or a level 0 or a high level or a low level. But what we are saying is, in terms of EMI, use as fast a rise time or a fall time as is necessary to get the required function, for the function to give you the required or the desired application, rather than making it better than it should be. Say, for example, if an application can use a clock speed of 100 megahertz, there's no need of putting there a clock of 500 megahertz, okay? If it can tolerate a rise time of 10 nanoseconds, there's no need of making the clock or the signals to go to 5 or 1 nanosecond, okay? Just give it as you can for you to make sure that you avoid the crosstalk issues. So we have to double or multi-layer PCBs should be used in the PCB design, and this will therefore create a conductive shields, okay? Because usually one of the side of the PCB will just be dedicated to a ground plane, and the circuit or the circuit elements and traces will be put on one layer. And therefore, if we have a multi-layer, most of those ones will be, the inner layers will be power and ground layers, while the component layers will be the ones outside, so for ease of connection. And then this will be interconnected using what we call via holes. So how do we ground and how do we reference a given value? Because we know that from circuit theory we can never measure or we are not interested in the absolute potential of a given circuit point. All we are interested in is what is the difference or what is the potential at this point with reference to this other point. And in many cases, you have that that symbol in circuits that is aligned with some short value, which looks like an arrow that is made of layers. Okay, and you have always called it the circuit ground. Okay, the circuit ground doesn't mean that it has zero potential with respect to another place. It only says that all the voltages in this circuit are going to be measured with respect to this point where that symbol is put. Okay, it doesn't say that that symbol represents 0 volts. So in EMC jargon, that is in the language of electromagnetic compatibility, ground or earth protection will be referred to as the system reference, or SR, which defines the central point in a circuit that will be used to check all other signals. The signal reference will often be defined as the supply, which is usually connected to the earth protection. Whereby earth protection, of course, is that when you look at your cables, that is your power cables, even on your computer, you'll see that you have a 3-pin plug with a long plug, of course, usually written there as earth. This is connected to physical earth and is there for your protection, so that should there be a short circuit in your system, then a large fault current will flow to the earth and then a fuse will blow. So the SR will generally carry many currents going in and out of it. And hence, we must locate this on the circuit as appropriately. Okay, you don't want it under some kind of components. You want to put it somewhere where that it will cause less interference. 2, its impedance must be made as low as possible. For those of us who will be doing electrical wiring, you will see that many of the times the earth of your house will be connected to a thick copper rod, which we call the earth rod, and then it will be hammered into the earth itself. And we must make sure that the connection of that earth rod and the earth is as low as possible, and therefore there have been materials that have been designed called the ground enhancing material, or GEM, that you may be forced to put there, especially if your area where you are building is in a rocky area or a sandy area. Sand is not usually doesn't have a very good conductance. So any EMI signals in its neighborhood must be kept as low as possible. And usually you'll find that some of the time there will be an empty, whereas the connection will be cut across it. That is, a groove will be made around some of these things to try and keep the EMI signals pass longer. So from the EMC point of view, the location of the circuit or the system reference depends on the circuit, the level of circuit emission, how the circuit immunity, how immune is it to interference, what are the circuit conductors, that is, how good are they, or how are the components placed on the circuit. Say, for example, if you have your analog circuit or low frequency circuit, then you have high frequency circuit in the path, directly in the path of the others, and then you have the low frequency circuit at the output. What would happen is that these are going to cause a lot of interference. And therefore, you want to make sure that you separate, that you never put the high frequency circuit in between two low frequency circuit portions of your system. So, as advice, you are asked to use a star connection of participating boards. That is, if you have several boards or several PCBs, you make sure that they are connected to the ground in star formation, okay, for the supply and the system references as well. And this will provide a lower impedance system reference and eliminate large differential current loops or ground loops. We connect short cables on one side of each board for the best performance. You don't want to put very long cables to feed the other side. Okay, there are very many of us who like putting a connection to, say, a bus bar, so to speak, and that bus bar may cause a lot of problems as well in terms of the EMI. So similar components should be grouped close together. By similar, we are saying components that are in the same frequency range. Say, for example, if you are dealing with analog components, put those analog components as close together as possible. Digital components should be put as close as possible in a separate, spatially separated from the analog side. So when you are using mixed signal designs, okay, to share the common ground plane, e.g., you group analog components and group high frequency components close to the connectors to reduce the line inductance. Then group digital components and use the slowest components that you can get away with. Okay, don't go for the very high end because you have the money and you want a very good device so that you can you have the bragging rights that you have a very fast system. That could be causing you problems as well. So separate digital and analog circuit ground planes as well when this is possible. And say, for example, analog to digital converters will have digital circuits that share the analog circuit ground plane. However, this is something you have to remember, and therefore you have to tolerate some of the interference that will be coming from this signal as well. So the antenna effect. The most important parameter of a cable is usually its characteristic impedance. As we have looked at, we were only looking at the characteristic impedance of the cable and its power handling capacity. So since cables and connectors will act like antennas in a circuit, then in view of the EMC rule for emission and immunity design, we have to place these cables and connectors on one side of the PCB and as close to each other as possible to reduce the area or the loop areas that will be looped by any fields that are generated. We keep in mind the effects of parasitics such as resistors, that is resistances, inductances, and capacitances will behave like RLC networks at high frequencies. That is, the effect of parasitics. We have that the resistors will have, of course, the conductor, the conductive part, which gives you the resistance. Then the resistance, the resistor itself, which is in form of a rod, maybe on one side it will be having the input lead, which will be at a higher potential than the output lead, and therefore the separation of those two is a capacitance over the resistor. Then we have another capacitor between the signal line, the input lead and the ground potential, the output lead and the ground potential if it's floating. And then if you have long leads, like most of us are used to making the circuits in the lab, where we don't want you to cut the leads of the resistor so that the next class can come and use it. Of course, when you are dealing with a system, you are putting it there for not to remove again. Therefore, you have to make those leads as short as possible to reduce the inductance, because the current flowing through the lead will generate a magnetic field. And therefore, all these values, all these parameters that we use in our circuits, resistors, inductors, and capacitors, will behave like RLC networks at high frequencies. So we must use as wide a bandwidth as the application requires. Say, for example, for many of us, when we make an amplifier, on an audio amplifier, we've been told that an audio amplifier or the audio range of the sound is from about 10 megahertz to 10 hertz to 20 kilohertz. And therefore we'll make our amplifier to amplify very nicely from 10 hertz to 20 kilohertz. But most of the time, most of the information is usually in the lower ranges, and in the higher ranges is not so much, because those ones are the ear just uses to put in the detail. So instead of making it that large, what we'll do is that we are going to make sure that we just use as high a bandwidth as the application will require. Say, for example, if we are making it for a hearing aid, an amplifier for a hearing aid, most of the information is intelligible up to about 3 kilohertz, and that's why the telephone line usually has a bandwidth of about 3 kilohertz. So if you add more for broadcast, we just need up to 5 kilohertz. Okay, so you don't have to make that amplifier for the hearing aid to go all the way to 20 kilohertz, because the person can listen or can hear all those. Okay, so we create a low impedance reference layer on the side of the board that will be carrying the cables and the connectors. So we keep in mind that each PCB trace is also an antenna for the interference signal, and therefore we have to use a shield. If we are going to make a shielding material, we have to make very small holes. Okay, usually you need holes for putting in the cables, and you also need holes sometimes for letting the heat that is going in, that is being generated by your circuit, to ebb out. So usually you use small holes rather than making one big one, because for those of us who can follow, before we talked about aperture antennas, these holes, if their dimensions are of the same order of magnitude as the highest frequency that will be processed by that system, they will be radiated by those holes. Okay? Even your windows in the house, there is a frequency that will be radiated out from that house, so to speak. So the holes required for the incoming cables or the heat transfer will be aperture antennas, and hence we use many small holes rather than using one big one. So keep the straight parts of the traces as short as possible. That is, if the traces are straight, they'll form a dipole. And therefore, if we make them as short as possible, okay, then it means that the frequency at which, or the wavelength at which, that straight portion of the line will be radiating efficiently will be very, very short, and therefore may be outside the range for which we are dealing with, that we don't want to have interference in. So we use 45-degree bends in the traces whenever we want to make a bend, that is to change direction of the trace. E.g., for example, a trace of length 0.6 millimeters will resonate and radiate very strongly at around 5 gigahertz, because the F is going to be given by the speed of light divided by the length, where the length there, L, is that the length of the trace itself, and C is the speed of light, while F is the operating frequency. Therefore, we reduce the longest trace to about 0.18 millimeter, and this will push that wavelength or frequency to about 16 gigahertz. This may be way outside the range of your circuit, because if you are dealing with a clock of, say, 200 megahertz, this would be a very high order harmonic, and therefore it will have, with the square waves having a harmonic of one over the harmonic level square, then you will find that the value or the power in that harmonic that will be at 16.6 gigahertz for that clock will be very, very small indeed, and will be below the regulated level of power that it should given by the standards themselves. So we now look at what we call EMC guidelines, and now I'll stop here for some minutes and let you have a breather or ask any questions that you might be having for now. So in case there are no questions, then take a 5-minute break. They will meet at on the hour. Is that okay?
Yes.
So we'll meet on the hour, just contemplate on what we have just talked about, and then we can look at the guidelines themselves. What do they say? So, welcome again. We'll continue from where we stopped. So, we look at the guidelines for the EMC. So, the EMC guidelines will specify the measurement techniques and the limiting values of the test severities for both the interference emissions and the interference immunities of the electrical equipment, installations, and systems. By installations, we mean places like substations, things like base stations or radio stations and the likes, or radar systems. The equipment will include my rotatory or rotationary or rotary equipment, any equipment that is using electricity, so to speak. So the European standards, since Kenya can barely be considered to be a manufacturing country, so most of our equipment are actually made outside, and therefore we are just importing. So most of the times is that we have to tell, okay, that is the people involved with the standards will ask the manufacturers that for any equipment you ask to sell in Kenya must meet the following standards, and most of the standards will be mainly adopted from the European standards, because today, like I mentioned yesterday, Kenya is a member of the International Electrotechnical Commission, and therefore most of the standards developed by the International Technical Commission, Electrotechnical Commission, will be adopted into a Kenya standard that is usually maintained and guided by the Kenya Bureau of Standards. So, the basic standards will contain information on the interference phenomena and the general measurement methods. That is, you are defining what those interference phenomena are and how should they be measured, because we know that different means of measurement can measure those quantities to different accuracies, so to speak. So the equipment that is not covered by the basic standards are then treated under what we call generic standards. That is, the generic standards will borrow some of the standards there and, so whatever, specialize them for those particular equipment. A study of this, this is what we are going to determine in this particular value that we are dealing with. So these documents I've shared with you in the Google Drive. That is the PDF document, EMC regulations, for your perusal, and also a presentation by Henry Benitez, giving also EMC regulations as well, if you want any further information on EMC standards. So the goal of EMC is to design the EMC guidelines is to design electronic systems that are electromagnetically compatible with their environment. So EMC requirements exist in the following way, so that the electronic system designers will have a set of guidelines that will explain the limits of what is considered electromagnetically compatible. So, however, an all-encompassing set of EMC guidelines does not exist, and therefore EMC guidelines are created by individual product manufacturers and governments. So the requirements are set forth by the government. The requirements that have been set forth by the government are usually legal requirements, and the products must meet this. That is, there are those ones which the manufacturers will put on their equipment so that they can always brag around that our equipment is very nice compared to this other competitor and so forth. But there are those ones which must be met that have been set forth by government, so to speak. So requirements that are set by the manufacturer are usually called self-imposed, and usually because the manufacturer will lose face if his product fails on the market, and therefore have monetary loss, those standards are usually more stringent than those ones that will be set by the government. So not all countries have the same EMC requirements, however. So each country will then be responsible for enforcing their own set of requirements, but this does not imply that each country has a unique set of EMC requirements, however. So various EMC requirements that are set by all countries will be very similar, and many countries now are moving toward an internationally agreed standard for EMC requirements as covered by the CISPR, which is a standards committee with that deals mainly with radio communication. This is a French word, so I'm not going to pretend to give the actual meaning, but it's a Comité International du Système something, standard something. Okay. So these standards were developed in 1985 by CISPR, or the International Special Committee on Radio Interference, and have been adopted throughout. The CISPR is a committee that has been set by the ITU, or the International Telephone Union. Okay, and most of these standards have been adopted by the European Union. But what I need to say on the onset, the CISPR and IEC have a working relationship, and therefore most of the standards are now going to be merged together with the IEC standard. So in the United States, the Federal Communications Commission, or the FCC, is the one charged with the regulation of radio and wire communication, and the corresponding authority in Kenya, so that we can put ourselves in a correct place, is what we call the Communication Authority of Kenya, or the CAK, and formerly it was called the Communication Commission of Kenya. This is an unfortunate kind of value, because we also have another organization in Kenya with the same initials, that is the Consumer Association of Kenya, or something like that. So radio frequency devices are the primary concern in EMC, and are defined by the FCC as devices that are capable of emitting radio frequency energy by radiation, conduction, or any other means, whether you are doing it intentionally or not. So the FCC will define radio frequencies as frequencies in the range from 9 kilohertz, that is in the shortwave ranges, that is the long wave ranges or medium wave ranges. We know that the medium wave is around that 1.5 megahertz or something like that, to 300 gigahertz or 3000 gigahertz, or what you'd call 3 terahertz. Some examples of radio frequency devices will include the digital computers, which we use. Today, many of the computers are running clocks in the 2.5 gigahertz clock speeds, and therefore the harmonics, if they are leaked out, would be very high frequency, signals. Blenders that have DC motors and brushes, and most of the drive today in manufacturing of DC motors for use in the house appliances are towards the brushless DC motors, because the arcing as the armature is leaving one conductor, one brush to the next, will generate very energy in the radio frequency range. Television sets that employ digital circuitry will also be generating radio frequency in radiation, and practically all digital devices that will be therefore regarded as radio frequency devices in the understanding of FCC and many of the EMC regulating authorities. So, with the advent of digital computers and other digital devices becoming popular, the FCC has realized that it is necessary to impose limits on the electromagnetic emissions from these devices in order to minimize the potential interfering with radio and wire communication. But the interfering, now the desired application is radio and wire communication. Now, if you have other devices dealing with emitting interference signals, they will interfere with the intended. And that's what we were talking about when we were talking about this, the division of the electromagnetic spectrum. There was certain bands we call the ISM bands, that is industrial, scientific, and medical bands, or ISM. And these were bands in which any other person who wants to use them would have to tolerate any interference that would come from the equipment that is authorized to work in that band. Okay? And therefore, things like Bluetooth, which operate in the 2.4 to 2.5 gigahertz ISM band, must tolerate that the interference that would occur from a medical equipment or an industrial appliance. Okay? They cannot go complaining that they are being interfered with. Okay? Although they are authorized, they are allowed, they have been allowed to work in that band. So as a result, the FCC now has set limits on the radiated and conducted emissions from digital devices. So as defined by the FCC, a digital device will be any unintentional radiator or device or system that will generate and that generates and uses timing pulses such as clock pulses at a rate in the excess of 9,000 pulses or cycles per second. That is more than 9 kilo per cycles per second, and uses digital techniques to process whatever the signals. So all electronic devices with digital circuitry and a clock signal in excess of 9 kilohertz will therefore be covered under this rule, with a few exceptions. So the law makes it illegal to market digital devices whose conducted and radiated emissions that have not been characterized, that is measured and verified to be within the limits set by the FCC. We shall see some of these limits when we look at the standards and standardization. So this therefore means that the digital devices that have not been confirmed as passing these requirements cannot be sold, marketed, shipped, or even be offered for sale in that particular jurisdiction. If you recall, when we were making the transition from analog TV to digital TV, terrestrial broadcast TV, there was things that there were terms used as type approval and the likes. This type approval was to make sure that the intended equipment would adhere to our regulations within our jurisdiction. So although penalties for violating the regulation will include fines or jail time, companies are usually more concerned with the negative publicity that would occur once it becomes known that they had marketed a product that fails to meet the FCC regulation. From an electrical point of view, say for example, an electrical point of view, I don't know whether you remember or you heard of this case where there was this company, Japanese company, that was making airbags, and a few deaths were reported when the airbags were operated in minor accidents, car accidents, and they had to recall a lot of cars from the market. And this company really suffered from that as everybody was moving out. Another case is when some of the vehicles had to be recalled, such as the VW, that is the VW, because of cheating in the standards of emission standards. But the emission there, of course, was about pollution. But then the Volkswagen had a bit of a beating in their their image had a beating. So that's the same thing. So if you are going to make a circuit or a system and then you want to sell it to the Kenyan public, say for example things like the digital governors, speed governors for matatus and the likes, and then it was discovered that your product does not meet the standards, of course you you'll have to remove it from the market. And what would happen is that we'll have to work hard to try and show the people that actually this new product you have is now better than the one you had before. Those issues have been taken care of in this particular product. So this is why we are giving you this kind of talk about the EMC standards, because many of us are going to employ ourselves, or we are going to be employed in companies, and we have people that will be doing fabrication, and we want us to be able to make products that will be sold elsewhere. Okay? And this means that even if Kenya can allow so much emission, Uganda may not, and therefore when you're manufacturing for the other company, for the other country market, you have to meet their requirements. And we shall show why the standards committees are trying to come down to try and put the same set of guidelines, so that if you meet one standard in one country, you have met the standards in all the others. And therefore you don't have to be measuring your equipment whether it has passed the limits in your country, and the country X, country Y, country Z, and so forth. You'll just do it for one, and therefore it will be much cheaper, and the products are going to be much cheaper as well, and therefore it will have a bigger market. So if the product were already made available to the public, the company would then be forced to recall that product. Therefore, it is important that every unit that a company manufactures is FCC compliant. So the FCC does not test each and every module, however, but what it does is to go and sample, just like the InfoTrack does, sampling 1,000 guys to represent 49 million Kenyans, and they say that 90% of us have this opinion. So that's the same kind of thing that the regulator will go, although I'm using FCC, it should be understood to be the regulator. The regulator will go to a particular manufacturer production line, collect some samples. They go to the market, collect some samples from the markets, from the shops, and then test them and see whether there is any of the product that meets that doesn't meet the regulations. And if only one does, then the whole line will have to be recalled. So the FCC has different sets of regulations for different types of digital devices. One, there are devices that are marketed for use in the commercial, industrial, or business environments, and this will be classified as Class A digital devices. This one can have less stringent regulations or limits, because it's understood the people that will be operating those devices or those systems will be most likely competent people, that is professionals, and they will also have the means of trying to mitigate any interference issues that might arise with these systems. Okay, so these Class A limits are usually less stringent than the Class B limits, which are devices that are to be used in residential environments, okay, notwithstanding whether they be used for commercial, industrial, or business environments as well. Okay, many of the computers that we have will be classified as Class B devices, because they'll be found with almost everybody, including small kids today. So regulations for Class B devices are more stringent than those for Class A in general, and it's because most of the time the devices will be in closer proximity in the house. Say if you are in a family of 4, each one of us will have a mobile phone, and therefore we have 4 digital mobile phones in the same environment. That is a small house of, say, a 2-bedroom house or a 3-bedroom house, if you have the means. That is, if you are not a hustler, so to speak. Owners of the devices are also generally less likely to have the skill and the resources to correct any potential problems that might arise. And a comparison of the Class A and Class B conducted emission limits are as illustrated below. That is, we have the voltage, the interference voltage in microvolts, and we have the frequency in megahertz. So for class A, we are allowed about a millivolt, okay, up to about 1.705 megahertz. And then above that, we can generate 3 millivolts. The device can generate 3 millivolts of interference. For class B, we have a flat requirement of about 250 or 0.25 millivolts for all class B devices. That is under the FCC limits, all the way to 100 megahertz. So it can be clearly seen that the regulation for class B will therefore be much stricter than those of the class A. So personal computers are a subcategory of class B devices and are regulated more strictly than other digital devices, in which computer manufacturers are then required to test their devices, and they must submit the test results to the FCC. You just don't test and put a flyer, or I'm sure you have bought a Chinese equipment and you have looked inside the package box. There will always be, say for example, there will be a flyer or a one-page document showing how they have tested it, or what kind of standard it has met. And some of them are usually not even very informative. And those ones are usually those ones we call that the illegal imports or something like that. So no other digital device require that the test data be sent to the FCC, and the manufacturer is usually only expected to test the devices to make sure that they are actually EMC compatible with the FCC policy, will then be policing the industry through testing of random products. That's what we talked about before. That's what we call market surveillance. So conducted emissions are the currents that are passed out through the power cord, that is the AC power cord of the digital unit, and they are then placed on the common power grid. Because all our houses, the electrical wiring is getting the wire from the power from the grid, and therefore, if we are generating harmonics in our house, these harmonics will be conducted along the power cord that is connected to the ring circuit or on the walls, and that will therefore leak back onto the main line and sent to the next guy downstream or upstream. So the conducted emissions are undesirable because once the currents are in the building wiring, they will radiate as well very efficiently because the wiring will be large, since the wire will have a very long length covering the whole house or the whole building. Then it will act as a very nice antenna at those frequencies, even if they are power frequencies. So the wavelength will be almost the same as on the same order of magnitude as the wire. So the frequency range of conducted emissions will extend from 450 kilohertz to about 30 megahertz. And remember, the 30 megahertz is the limit of the shortwave radio. So devices are then tested for compliance with conducted emissions and regulations by inserting into the line a component called the line impedance stabilization network, or a LISN, into the AC power cord. The current then passes through the AC power line and into the LISN device, which then will measure the interference current and will convert this current to a voltage for the measurement. So the actual FCC regulation will then set the limits on the voltage from the LISN through, although it is the current that will be actually be regulated. That is, we regulate the current because the current, if you recall, current is the one which causes radiation, okay, or sets up the electromagnetic fields, okay. So the current distribution is more important, but it's the voltage that will be measured instead by the LISN device. So radiated emissions are the electric and magnetic fields that are radiated by the device that may be received by other devices and therefore causing interference from those devices. Just like the problem we were appraised of yesterday by one of our colleagues, of the laptop causing interference with radio reception. So although radiated emissions are both electric and magnetic fields, the FCC and other regulatory agencies usually only require that you measure the electric field for the certification for compliance. So the magnitude of these fields will be measured in dBm, dB per millivolt per meter. That is, we reference all our measurement to 1 millivolt per meter, with the frequency range for radiated emission extending from about 30 megahertz to about 40 gigahertz. So radiated field measurements for FCC compliance are carried out either in a semi-anechoic chamber or at an open field test site. That will go out where we'll not have any reflections, and then we'll measure our fields. Or we can bring them indoors, then this indoors, the room will be coated with an electromagnetic absorbing layer or coating, so that there are no reflections there as well. And therefore, the only thing we'll be measuring is only the incident wave on the measuring antenna. You know that, if you recall, that if you have reflections, we can set our antenna at a node where we have destructive interference, and the fields that we'll be measuring there will be less than the maximum that the system is producing. So the product under test must then be, by stipulation, it must then be rotated to point to the antenna such that the maximum radiation is achieved. That is, we are trying to match the radiation, that is the direction of propagation of that radiation, and the antenna that will be receiving that radiation. That is, they are polarization matched. So measurements must be made, one, with the antenna oriented in the vertical direction and also oriented in the horizontal direction, so that we can get the radiation from both direction principal planes of that antenna. So the measurement method for radiated emission will depend on the type of device that is under test. So for Class A digital devices, this must be measured at a distance of 10 meters from that device. Because at 10 meters, of course, we know that with the 1/R reduction in the amplitude of the electric field intensity, then we are usually actually measuring a lower value of that radiation. But since we were stricter for the B, this will be measured at about 3 meters from the device, because we want to make sure that the values that we are obtaining from that device are much lower than those that will be coming from the Class A. So the radiated emission limits, as defined by the FCC for Class A and Class B, would be as follows. For Class A, with that, we have a flat value of about 49.5 dBm or a dB microvolt, okay, up to about less than about 100 megahertz, about 88. That is the beginning of the FM range. Then we'll go to a higher level of 54 and so forth in statewise. Okay, so if you are making your equipment, you have to make sure that you measure its radiation under 100 megahertz, and it has to be less than 49 for industrial use, or if it's a Class B one, it has to be below 40 dB per microvolt, with reference to a microvolt for the range 30 megahertz to 88 megahertz. Then it can produce more than that, okay, in this frequency range, 88 to 216, but it should be no higher than 43.5, and so forth as you go along. But this becomes easier to implement because, as we said, the fundamental will be mainly in this region, So you want to make sure that the third harmonic of a digital clock is below this value. If it's below this 88 megahertz, that it has a value of less than that. The fifth one will have an even smaller, and therefore the third one will be it should be below that as well. That is, the fifth one should be below that 43, and it's much easier to implement. So, because the measurement distance defined for the two measure requirements are different, we must scale the measurement distances so that they are both at the same distance in order to achieve an accurate comparison. So to do this, the inverse distance method is usually used, and this assumes that all emissions will fall off linearly with increasing distance to the measurement antenna. And hence, emissions at 3 meters will be assumed to be reduced to about 3 by 10 if the antenna is moved further out to a distance of 10 meters. So to translate class A limits from a distance of 10 meters to 3 meters, we are going to add 10 times the logarithm of 3 by 10, and we get a value of 10.46 dB. Of course, this is negative, so we'll get a lower value, and then we can therefore compare the class A limits, the class B limits, which are measured at 3 meters. So this approximation is only valid if the measurements are actually in the, that is, if 10 meters is in the far field of the emitter, okay, that is your equipment, okay, or the 3 meter is in the far field of the emitter as well for the class B. So we can assume that the far field boundary is 3 wavelengths from the emitter. And hence, with the radiated emission frequency range defined as 30 to 40 gigahertz, the maximum distance from the emitter for a far field measurement must be 30 meters. Rarely will you get a room that is 30 meters wide. Okay? You can do this in the open field, but in the indoors, it's usually impossible. And therefore, even the 10 meters that we use for all measurement, they will be in the far field only for frequencies that are above 90 megahertz, okay, at 10 meters. And hence, the inverse square method can be assumed to be accurate only for these frequencies. However, the comparison, of course, still demonstrates that the class B limits will tend to be roughly 10 dB more stricter than the class A radiated emission requirements. So although each country is responsible for its own set of EMC regulations, the CISPR regulations have been adopted by several countries, and a comparison with the FCC regulations in the United States may aid understanding of the standardization process. The CISPR 22 regulations, we have seen that has been adopted mainly in Europe, but now everybody else is going towards that, and this will require that the radiated emission measurements for class A devices be at a distance of 30 meters and 10 meters for class B. And the measurement limits are scaled to a common distance using that inverse distance method we have talked about, and the plot of the CISPR 22 and the FCC regulations will then be put together for comparison. Although the regulations will vary slightly in different frequency ranges, then there are no significant differences between FCC and the CISPR, which is used mainly in the rest of the world. So the CISPR 22 regulations can therefore be established for radiated emissions as shown in the graphs to be the graphs for class A and class B respectively. These are the values that we have here, and this for class A, we have the FCC standards, okay, in complete line, and the CISPR, which is flat all the way to 230 megahertz, and then goes to another value which is very high. For this particular case, the differences is what we are saying are not very significant. And we see that the CISPR 22 regulations may be much easier to regulate, but we can see they are stricter and the FCC below 230 megahertz. For class B, again, we have a similar value. This is coming from the FCC, and this is coming from SPR. And here, all of them, the measurements have been put to 10 meters from the emitter. So the differences, the FCC and the CISPR, the 22 regulations are more apparent for conducted emissions and emissions limits, with the differences in the regulated frequency range being the most noticeable. So the maximum frequency is 30 megahertz for conduction for both FCC and CISPR 22, and the CISPR regulation will extend down to 150 kilohertz, and the FCC does that, regulates only up to about 450 kilohertz. So those limits for class B will rise steadily for frequencies below 500 kilohertz, and the rationale behind this extension is because of the increasing importance of switched power supplies in the industry and also in the residential areas over the linear analog ones, occasioned by the higher efficiency and the lightweight. You want to have a light power supply, you'll find that it's much easier to get a smaller transformer if your frequency, the frequency of the AC supply is higher. So what happens is that you will rectify the AC mains at 50 kilohertz directly, and then smoothen it to a rough, a high ripple kind of DC voltage. Then we will use a chopper, that is a switching circuit, to chop that DC, rough DC, into high frequency pulses, sometimes up to 200 kilohertz, and then use a pulse transformer, which will be much smaller, and therefore you don't need a magnetic core. You can use even an air core to drop them down to a lower value, and then you can therefore use the rectification again and smoothing, and you'll use a smaller capacitor to smooth that to get the DC. So the CISPR 22 regulations for conducted emissions are specified using a quasi-peak detector and an average detector. That a quasi-peak detector is like you are using a capacitor which charges to the maximum, to the peak value of the waveform, and then you measure those values there. The average one is the one which is using rectification, like we have in AC meters that we have in the labs. So the FCC conducted and CISPR and FCC radiated emission limits will require the use of a quasi-peak detector. They don't use an average detector. So between the FCC and the CISPR 22 regulations for Class A and B devices will then be as illustrated. So we have those values there for the CISPR using the average detector, and then the FCC, of course, we have that, and the peak detector values have been given as that form there. So Class B devices will have those kind of variations for the comparison for the conducted devices. So because of the great importance of EMC issues in military applications, to ensure that missions are not compromised, the military has developed military EMC regulations. And some of the regulations, even in the aviation industry, where a problem arising can be a very high cost of both equipment and human life, the regulations are much more strict in this particular kind of applications. So in addition to regulating both the conducted and radiated emissions, the military also requires that the susceptibility, which is usually very important, okay, must be also be regulated. Military equipment must be of essence, be immune to outside interference, because the enemy will also be trying to jam the equipment itself. And you want to make sure that that equipment we will be able to work even under an environment with hostile radiation, such as jamming signals. So the military EMC regulations are more stringent than the FCC or the CISPR regulations and will cover a much wider frequency range with several subdivisions within this range. And in addition, the military may require that EMC requirements be waived for certain applications if these are deemed necessary for mission success. So on the other hand, CISPR and FCC regulations cannot be waived for commercial products at all. So how do we measure these radiated emissions for compliance? To ensure testing for radiated emission is accurate, the FCC and the CISPR have developed testing standards that will explain how the test must be carried out to verify compliance, to ensure testing is both accurate and repeatable throughout. So the radiated emissions, the FCC specifies that the measurement of the radiated and conducted emissions must be performed on the complete system. All cables interconnecting to the peripheral equipment must also be connected. So if it's a computer, desktop computer, you have to connect all the equipment that will be used for that computer to work as a computer. We are not talking about those other things like maybe a music system or some an active an active speaker system and the likes, but we are saying those things like if you have a wired mouse, the keyboard, the power supply, the display, the computer unit itself, and so forth, must all be connected together when you are testing that equipment for the compliance. The system set has to be in the typical configuration that is going to be used in. And both the cable and the system must be configured in a way that will maximize any emissions coming from the equipment, so that we are measuring the worst case scenario. And if the worst case scenario is below the limits, then the whole system is compliant. So for example, if the unit under test has interior wire harnesses, that is things that are tying together the interior wires, these harnesses must be configured in such a way that of all the possible ways the unit can be assembled with those wire harnesses, that the way it has been assembled is the one that will cause the maximum radiated emissions. And this will therefore ensure that when the unit is mass produced, the worst case scenario will have been taken into consideration. The testing standards that are set forth by the FCC for radiated emissions testing are very specific, and they are usually very difficult to automate. And the radiated emissions are to be measured at 10 meters for Class A and 3 meters for Class B. And these measurements are to be made over a ground plane using a tuned, that is, we are specifying even the antenna that we are going to use, and even the position where this measurement is going to be carried out. That is, has to be a tuned dipole antenna that is tuned for the frequency it's supposed to receive, and the measurement must be done in the open field. In addition, the tests are to be made with the measurement antenna in both the vertical and horizontal polarizations positions. And during product development, most companies will test their products in a semi-anechoic chamber because of most of the industry don't have an open site where you can get 30 meters. We'll use it now in an anechoic chamber, which is a shielded room with the radio frequency absorbing cones on the walls and the ceilings to remove any reflections from the walls. So an example is as shown below. These are the cones we are calling the absorption cones. They are made of, that is, they absorb and dissipate the power in there in a pointing, kind of a vector kind of way. Then we also have the height of the dipole or the antenna that we'll be using, this is a biconical dipole we are talking about here. The scan height is about 1 to 4 meters for both vertical and horizontal polarization above the floor. You have a spectrum analyzer not inside the chamber itself, and you have your DUT, such as a computer display, which I'm using here, not the common LCD ones, but the earlier ones, which were actually a tube, you know, like such as the ones you get in oscilloscopes. And this will be the shielded room that we are dealing with. So the semi-anechoic chamber simulates an open field by absorbing the incident wave, and therefore the wave coming from the aggressor will tend to think that the walls are infinitely far away. Okay, and this will also eliminate any other ambient signals that may be present in the open field environment. So companies sometimes will simplify the FCC test procedure using a broadband antenna, such as a long periodic antenna or a discon antenna, like I've shown in the example, the diagram. And such antennas are desirable because since a tuned dipole, you have to go in there and tune it again to the frequency that you are testing. The length does not have to be changed if it's broadband for each frequency change that we effect. And therefore, the companies are therefore allowed to test their products, enabled to test their products using a frequency sweep. That is, your generator, you can send the excitation to your device under test, okay, and run it. It will radiate in all those frequencies, but now we can just sweep the antenna over those frequencies rather than doing it, measuring at every frequency separately. So in addition, an additional testing requirement for radiated emissions testing is that the bandwidth of the measurement receiver must be at least 100 kilohertz so that you can get nice resolution. So a wider receiver bandwidth ensures that the test will pick up emissions from broadband sources, such as the arcing at the brushes of a DC motor, in addition to the intended narrowband signals, such as clock signals. So the FCC and the CISPR test procedures require that the measurement receiver use a quasi-peak detector, while typical spectrum analyzers will be using peak detectors. That is a diode to rectify the envelope and a capacitor to smooth that and convert it to a smooth voltage value to be measured. So quasi-peak detectors usually ensure that there is fast changing momentary signals, such as randomly occurring spikes, will not charge up the detector to as high a level as a periodic signal would. So the FCC is concerned primarily with the more significant and frequent emissions that would cause interference with radio and wire communication, rather than with randomly occurring one-time signals. So the intent of conducted emissions limits is usually to prevent noise currents entering the common power net of the installation through the AC power code of the device. Because you know that many times there are many different kind of loads that are getting power from there, such as lifts and motors within the house, and we know that motors have different characteristics. If your signal has a high harmonic content, the lifts as well will be interfered with. So the common power net can be regarded as a large antenna, and any noise currents that are placed on it will be consequently radiated very efficiently. And an example is the interference that would be occurring on a television or radio set when you switch on an earlier blender type. That is a blender that was using the brushed DC motors. Today, like I said, most of the motors are brushless, like those permanent magnet motors and the like. So acting at the commutator of the DC motor in the blender will cause noise currents that are conducted through the power cord to the common power net of the house, and the wiring in the house will then act as an antenna and radiate this noise, which is then picked up by as an interference by the television and radio antennas. So hence, conducted emissions limits are concerned with these noise currents. So the FCC and the CISPR 22 conducted emission limits will specify voltages because the listen that is used to measure will convert all the noise currents into a voltage. And to understand the function of the listen, understanding the standard AC power distribution system is usually essential. So in the United States, we have AC voltages that are distributed to residential and business premises at 60 hertz and 120 volts RMS. Usually they will be put as line to line or single phase, or they will be put to line, that is, you get something like 240 between the lines. So in Kenya, our value follows the British value, that is, we have a frequency of 50 hertz, okay, plus or minus 1%, and a value of 240 volts. But today the new regulation is, of course, or the new standard is 230 volts RMS, okay, rather than the 240. But we have seen most of the equipment, you usually have plus or minus 10%. Today we are using plus or minus 6%, I think, and therefore it's something like 240 and 30 will still be covering the earlier value of 240 volts, so to speak. So the power distribution in the home is through a 3-wire cable consisting of a phase wire, which is usually brown, a neutral wire, which is usually blue, and the green and yellow striped wire for the earth. So both the phase and the neutral wires will carry 60 hertz of power or 50 hertz power, and the potential between each wire and ground will therefore be equal to 120 volts. So the currents that must be measured for a conducted emission tests are the currents that will be occurring in the phase and neutral wires. And the listen that is used by the FCC conducted emissions test will be as illustrated below. So we have the product and the test. We have the line, neutral, and ground going into the listen. Then we have the phase wire going up with a choke, and the neutral wire going in with its own choke, and therefore we are using that value. Then from the phase wire, that is the phase line, we have a capacitor C1 that will connect to a resistor R1 and a 50 ohm dummy load, okay, and another, and also the neutral wire, we have a capacitor C2 connected to R1, a similar resistor just like that at the dummy load, and we'll be measuring the voltage with respect to the ground to the green wire, okay, that is developed by the currents from the neutral wire. And that will be the currents developed by the phase wire, and then that you can see it's a pi network for all of them, okay? That is a pi network. We have that C2 there and C1 there coming to that value. And then this will be the AC network of your, that is your port connected this to the power point, which may be the socket. So a similar listen is also used for the SPR 22 conducted emission testing as well. But however, the component values for the conducted emission testing are usually different because the different frequency range that are defined for CISPR for conducted emission testing. So the two functions of the listen are as follows. We said there were line stabilization network. So the first one is to isolate the external noise from the common AC net from contaminating the measurement. Two, to present a constant impedance in frequency from site to site and to the product between phase and ground and between neutral and ground. So the operation, when it's operation, one of the 50 ohm resistors will represent the input impedance of the spectrum analyzer, while the other 50 ohm resistor will be a dummy load. So the 100 microfarad capacitor C1 will block DC so as not to overload the test receiver. Resistors R1 are rated at 1 kilowatt and will provide a DC path for C1 to discharge if the 50 ohm resistors may become disconnected by some means. So the device under test should operate normally at 60 Hertz or 50 Hertz for the European and Kenyan scenario, and hence the capacitors are dimensioned to make them appear as open circuits at the power frequency, while the inductors appear as short circuit at these power frequencies, that is 60 or 50. The equivalent circuit of the listen at 60 Hertz will therefore have the following form. That is, we have a complete wire just connecting through to the AC network. So in the frequency range of conducted emission, that is 450 kilohertz and 30 megahertz, the capacitors will appear as short circuits, while the inductors will appear as open circuits, and we will have the following form. The inductors are very high impedance at those frequencies, so they are open circuited. Okay, they are out of the line. The capacitors are all short circuited, so you can see that all of them are short circuited, they go through, and we have that the test circuit now looking at that, and therefore we must be able to measure some voltages. So the currents on the neutral and the phase lines can therefore be isolated and measured at the 50 ohm resistance point. So the currents on the phase and the neutral lines have no path into the AC power net, however, as you can see. And we recall that the FCC and CISPR regulations are set by law to regulate digital devices. And individual companies will, however, that is, we are talking about additional product requirements, will impose their own set of regulations for their products, which we say is for their own protection. And these are usually more stringent. They want to be below, as much below the regulation as possible, so that their product will not have a chance of being outside those regulations. And the automobile industry, for example, exempt from FCC requirements, yet they have a self-imposed set of regulations that far exceed those set by the FCC. Okay, for normal digital devices. So this will be because companies face a far greater financial loss as a result of a faulty or poorly designated designed product, and they would, by investing to make sure that their product is safe and well designed and meets the FCC or the government regulated regulations. And people will put their lives in the hands of the automotive manufacturers most of the time, every time you drive your vehicle. And therefore, the automotive manufacturers cannot afford to have lax standards for this particular case. So apart from imposing stricter versions of government regulations on themselves, many companies will also impose design constraints on their products that must be enhanced as well. So they will ensure radiated and conducted immunity. That is, your equipment will not be interfered with when it's operating. The immunity against electrostatic discharge, that is any discharge that would come, okay, from say like lightning or the dielectric breaking down. Then FCC does not regulate these areas because they do not pose a threat to the radio or wire communication systems, and hence individual manufacturers are left to create their own standards for these cases. So each of these categories is associated with the ability of the device to function in the presence of the external circuit. And therefore, these are utmost importance for the manufacturers, and they must guard against them. So radiated immunity is the ability of the product to operate in the presence of high power transmitters such as AM or FM transmitters and airport surveillance radar systems. These are usually systems that are radiating very high frequencies in these environments as well. And two, manufacturers will therefore test their products by illuminating them. That is, you wash your product with these beams and see and measure the value and simulate the worst case exposure that product could encounter in its operational environment. Just like the same way you would heat up your device or your system to see whether it can operate in the usual places of high temperature, say for those of us who will go to work with the petroleum mining industry, we'll have to work with devices that can operate at high temperatures. If you are dealing with satellites, the temperatures up there will be very high during the day and very, very low below freezing in the night. And therefore, you want to have components that can operate in those wide ranges. So the same thing, you'll be facing the solar radiation when you're up there, and therefore will it interfere with the operation of your system or not? Okay. So conducted immunity, on the other hand, is the ability of that product to operate despite a variety of interference that may enter the device through the AC power cord. For example, for such interference, the power surge that would occur, especially when there is a lightning strike. Manufacturers must design tests that simulate the effect of the lightning-induced transients and design the product to resist such an interference. I have only one slide, so I request that you just allow me to go through and finish my sliding today, and then we can pick it up with the discussion from next week. So, electrostatic discharge describes the discharge of the static charge built up on the human body or furniture through a product when the person on furniture comes into contact with it. For those of us who have in the American wing, if you went down the stairs with your hand rubbing on the railing, the plastic railing, then when you get down and you touch a door handle that is made of a metal, you feel an electric shock. If you live in a carpeted house and you walk all the time, if you touch something metallic, you feel a shock in there. That is what we are calling electrostatic discharge, because you are building up. Many of the devices that we'll be working with, such as MOSFETs, they are usually very prone to electrostatic discharges. And most of the equipment that you buy, you'll find that they are usually put in a plastic, something looking metallic plastic, but it's a plastic bag. This is usually to keep out any discharge during storage. So such static charges can rise to as high as 25 kilovolts. And when the discharge, when they discharge through a product occurs, the large currents will momentarily course through that product and may cause the machines to reset, or the IC memories to clear, or you may get the device actually blowing up. That is, the transistor will break, especially for MOSFETs. The gate is isolated, and therefore when the dielectric, and that the gate has a very thin layer of silicon dioxide, and therefore when that high current flows through that dielectric, it will just break, and the gate will be connected to the channel below, and the transistor is history. So manufacturers will test their products by subjecting them to control ESD events and design their product to operate successfully in the event of such an ESD. Because when your machine resets, it means it will have to restart the program again, and therefore there is a glitch in the way in its operation. So, and this brings us to the end of that particular part. So next week we will be looking at the standards and standardization, and then we shall cap up our discussion with the topic on dielectrics, that is liquid and solid dielectrics. And then after that, we can now start looking at reviews and also looking at tutorial problems and how to solve electromagnetic transmission line and waveguide kind of, or guided wave problems that we are likely to meet in an exam environment as well as in the practice field. So with that, we come to the end of today's lecture. So I know I've maybe I've gone over the time by about 5 minutes. So I don't know whether there are any pressing questions. If there are none, then I propose I will wish you a nice weekend and we meet next week. God willing, as they say.
Thank you. Nice weekend to you too.
Okay, nice weekend then.